when a decision, so the way a decision tree decides which variable should be used to create a new branch or new split, it uses entropy. What is entropy? Entropy is simply a measure of randomness or surprise. The way entropy is calculated is, if you take the example of a coin toss where there is equal probability of it being a head and equal probability of it being a tail, you need to calculate first the probability of it being a head and the surprise in it being a head. So probability of it being a head will be 0.5, and the surprise is simply the inverse probability, so 1 upon probability of head, which will be 1 upon 0.5. But additionally, we will put this through a log2 function, which will give us a value, which will be, I think, around, it will be around a 1. So our result will be 0.5 into 1 plus 0.5 into 1, which will become 0.5 plus 0.5, which is equals to 1. So simply the entropy in a coin toss is 1, which is the highest possible. That means it's a completely random, completely random event, and there is no no exact, this anything could happen. That's what it simply means. Now the entropy was lower, like 0.5. That means there is a trend. A certain category is more present in this data than the other. So that is how entropy is used. So, so in some cases, so this result is called a leaf node. So how do we? Sorry, not this result. This these two rounded rectangles are known as leaf nodes, right? The prediction is made in one of the two leaf nodes. So when does a decision tree stop at a leaf node? So it stops at the leaf node in any of the below situations. All examples in the leaf node are correctly classified. Simply, in this case, all of the yes branch leaf node results are 0, and all of the right branch leaf node results are 1. So it's completely classified with 100% accuracy, and the entropy is 0. We cannot find an attribute to split upon. So despite the accuracy being low, we don't, or not good enough, or requiring further splits, we don't have any features left. We have used all of them. The split reduces the entropy less than the value. So we are trying, the split has reduced the entropy to the to the amount we want. We are not sure, or for some reason we do not want it to be split further. And finally, the tree reaches some maximum depth. We will define a depth for the tree, or not exactly we will, the model will itself find a depth for the tree, and then based on that, if it has reached that depth, it will stop at the current leaf node. Like it would be 50, so it could keep going for 50 nodes until it finally stops, right? So this model can be improved by techniques like backtracking, right? The most widely used formulation of a decision tree learning algorithm is called C4.5. It it is it has more features when compared to ID3, right? So the way it does that, it accepts both continuous and discrete features. So rather than saying that you give me only categorical features or you give me only continuous features, it accepts both, right? And it handles incomplete examples, and mainly it solves overfitting problem. This is the main use. It solves overfitting problem by using a bottom up technique known as pruning. So what is pruning? Once this tree has been completed and you have reached the result, what pruning does is it checks which branch is not helping significantly in the error reduction and removes that branch. Because as you are creating more branches, you are continuing to fit the model more perfectly, right? Because you are assessing more features. So and if some branching or some new split is not helping the model that much, you can remove it. Otherwise, if you try to analyze every feature despite it not helping your error, you have the risk of overfitting because you are training itself on more features than is required. Now, support vector machine. I already presented support vector. Support vector machine has already been introduced in the introduction. So let me just go back to that. Support vector machine simply is like linear regression, except the difference is that it works on multiple variables. So what the thing that it does is, instead of here you can see it's like linear regression, except the difference is that there are two differences mainly. First of all, it can work on multiple x features, so it creates a plane, a 2D, 3D, or based on the number of variables, an n-dimensional plane which separates our one category variable data points from our from our zero category data points, right? And one more thing is that it uses something called margin. So margin simply means, what it does is it wants the decision boundary to be placed in such a way that some area around it should be unoccupied, right? Because the closer you are to a decision boundary, the more your uncertainty increases. Because if you get if you get a data point which is right on the decision boundary, you won't know where to put it. So you want to create a decision boundary in such a way that the area around it is mostly empty, right? The way this helps is that if so far there hasn't already been a data point, another data point coming there, chances are low, right? And if there is another data point, then you adjust the margin, because you don't want it that your model is like giving you low confidence predictions. So that is what marginalization does, right? And how SVMs use their hyperplanes. Hyperplanes is simply an n-dimensional plane used for classification. So now let's get back to our SVM. So there are two problems that we face in SVM which we will answer. What if there is noise in the data and no hyperplane can perfectly separate positive examples from negative ones? And secondly, what if the data cannot be separated by a plane but could be separated by a higher order polynomial? So, dealing with noise first of all. So you can see here there are two charts, right? The first one here has noise in it, which noise simply means there are some data points which are either wrongly labeled or something, but they are in the extreme. I mean, like it's like a one, it's a data which should clearly have been predicted as blue but is red, so it's either an outlier or something, but it's called noise mainly, right? To deal with this, a hinge loss function is used, right? Hinge loss will, for like here, if you create a decision boundary, it will separate the red and blue data points in the first figure, right? And if a data point lies on the wrong side, on the right side of the boundary, it will give not there will be no error, the loss function will be 0. But if it's on the wrong side of the decision boundary, the error's value will be proportional to the distance from the decision boundary. So like this point is quite far away, our decision boundary will be somewhere around here between these two, and so the error will be quite high, right? And then we will try to minimize this cost function by using a parameter called C. C simply maintains whether you should increase the size of your decision boundary, should you increase the margin. If the margin is still here, then only these predictions will be, if the margin is ahead of the noise, right? If it's coming all the way till here, then only this group of predictions on the right hand side of the margin will be treated as absolute, while these will be taken doubtfully. So one thing could be that, right? The value of C is usually chosen experimentally, just like ID3's all the other hyperparameters. SVMs that So those that optimize, optimize simply means, try to find the perfect value for hinge loss, are called soft margin SVMs, while the original form, originally the hinge loss which is there is called a hard margin SVM, which doesn't try to, optimize or improve itself. And finally, dealing with inherent non-linearity. So the way you can deal with data point, like in this second chart where you can see only a polynomial which will make, a line around this blue cluster can deal with it. Our SVM model, how will it make a boundary that will separate this circle? The way it does that is it uses a function and it transforms the original space by adding a dimension. So this is a 2D chart. It has only two dimensions, right? The data points are based on two dimensions. It takes this and then converts this to a three-dimensional space, as you can see over here. So you can see the red dots data points are still in a circle. The blue data points are still clustered close together in a smaller circle, but now they are easily separable. All you need to do is make a two-dimensional plane, which is like a square. So a two-dimensional plane which separates the red data point from the blue data points. And this plane, this adding of a dimension and then creating a plane is called the kernel trick. Okay. So using this transformation of, using this transformation and adding a dimension, you are converting non-linearly separable data into a linearly separable three-dimensional data, right? By using some specific mapping, you will run some specific function on your x variable and define a new variable which you will use as your, third dimension, right? We don't exactly know which function or how we should change our x to get our third dimension. So usually our model will try all possible functions. I mean, if it does that, it will become very inefficient and we would never solve our classification problem. Fortunately, this problem has been figured out, right? There is a way in which SVM is optimized. So with minimum, uh, minimum with trying only a few methods or few different functions, our model is able to find out which is the best method to create this third dimension. And this is done by using a method called Lagrange multipliers. We will go into that in the future. Now let's get into k nearest neighbors. So k nearest neighbors is a unsupervised learning algorithm, right? And usually what other models do is once they have got this hyperplane or this decision boundary, they discard the data and only use the decision boundary to check where to create those predictions. But k nearest neighbors keeps those memory points in the keeps the data points in its memory, right? And once a new previously unseen example comes in, it finds which data points are which data points are closest to this point, to the x, and returns the majority label of those data points. So simply what it does is, in this case, suppose you get this blue dot, so blue data points, it will say, okay, what are the five, for example our key, we defined it as 5. So it will say, okay, what are the 5 closest data points to this new prediction x? So it will say, okay, these 1 2 3 4 and 5, out of which 4 are blue and 1 is red. So the majority label that is appearing is blue, so this is a blue point, so it will put it in this blue cluster. That's how k means k nearest neighbors works, right? The closeness of two examples is of course given by the distance function. One is like, there is a distance function known as Euclidean function, right? Another is cosine similarity, which uses the angles between the vectors for finding out which vectors are closer to each other. Now we will discuss about what goes behind a learning algorithm. So behind every learning algorithm there are three main components. There is a loss function, an optimization criteria based on the loss function, right? So simply how much importance should be attached to the loss. So it's also called a cost function, and an optimization routine which will just use the training data to find a solution. So these three. So simply one will calculate the error, one will decide which error, how much of the error should be given an impact on, and finally one will find the solution or the decision boundary based. If it's a supervised learning problem, this final part will find a decision boundary which solves our prediction or classification problem. So the first thing we will discuss is gradient descent or stochastic gradient descent. So let's discuss how gradient descent finds the solution to a linear regression problem. So for example, we have this data where you have sales units and spendings in millions of dollars, right? And so you have, okay, we made like how many number of sales units, how many numbers of units were sold and how much we spent on them. You can see as your spending is increasing, more sales are being achieved, right? So gradient descent is simply how our model decides what should be the values of the line. So the line has an equation y equals wx plus b, where w is the slope and b is the y-intercept. So we want our gradient descent to get us the best possible values of w and b, right? If there are more dimensions, obviously it will turn into a plane and we will have w1, w2 and w3, based on every angle of the plane. But let's just speak about two-dimensional data for now. So we want a line which best fits this, and for that we need to derive its equation. And the way gradient descent will do that is this is simply how much a company is selling units based on how much it is spending on radio advertising. Okay, so each row in the data set represents a specific company, so these are all different companies now. So and we have data of 200 companies, so we have 200 training examples, and our x variable is our spendings, y variable which we are trying to predict is the sales. Now we are trying to find the optimal values for w and b, and to do that we will look for the values which will minimize the mean squared error, right? And gradient descent will start with calculating, it will calculate w and b and the error and check, where is the w and which weights and bias has the least error, right? Which y-intercept and slope is giving us the least error. So it will calculate for the derivative for every parameter, right? And it will do this in epoch. So simply what it will do is it will say, okay, let's initialize our w to 1 and our b to 1, and it will check the error. Then it will decrease both value, it will subtract a small value, okay, w to 0.9 and b to 0.9. Then it will check if the error is decreasing, that will know it's going in the right direction. So it will continue to subtract the values until the error starts rising again. If that happens, it will go back to the value where the error was last at its minimum and select that as the optimum values for w and b. And this happens in epoch, simply iterations, right? So an iteration or epoch is when you use the entire training set to update each parameter, right? So you can use one training set multiple times. Yeah. So you can see here how in epoch 0 our line was in not exactly classifying, not exactly doing a good job. By epoch 400 it was doing a pretty good job, it was getting better by epoch 800, and finally, over time the difference in the line is getting less, because as you go on and on, the rate at which the model learns or adjusts itself decreases. So you can see, because you're getting closer to the minimum error, so there's only that much change that you can do before you reach the lowest possible error, right? Here you can see it's printed here in this program. We are defining average loss based on spending, sales, w and b, right? And we are calculating the total error, which we first initialized to be 0. And then for every time we calculate again, we are saying total error is sales of that record minus the weight into spending plus bias, right? Because it's y minus what we used to predict. So it's y minus y predicted. Our y predicted is simply a w into x plus b. So we are simply subtracting our y from y predicted and getting the error. So in our first epoch, our error was 92. Then 400 epoch, it was already 33. By our 2800th epoch, it was 19. So our error has decreased, by a huge amount. So this is how gradient descent works. Now, gradient descent, the amount by which it will adjust w and b at every iteration is known as the learning rate. And this is it is if you keep a very small learning rate, it is very slow, because if you have a large data set, it will take a lot of time. But there have been some solutions proposed to this, like for example, if for every time, and if you keep, so why would we even keep a small learning rate? Let's first understand that. If I want my model to learn fast, obviously I'm going to keep the largest learning rate possible. Why not keep it 1000? That is because if every time your model is going to adjust the weight by such a large amount, it will miss the global minima, which is the lowest point of error, because it is adjusting adjusting so fast, and by so much, it will jump right over the local minima. So for example, its error will be coming down in, like, first epoch it's like 90, second epoch it's by 200th epoch it's like 80, right, and so on. But it will never come close to 5. It will go to 10 and then start rising again. Okay, 20, 30, 40. That is because your learning rate was too big. You need to tone it down because you want your model to perform better. So you need to give it something like 0.01, something very small. But that will take too much time. So what is the solution to this problem? So there is something called mini batch stochastic gradient descent, or mini batch SGD. This is a version of this algorithm that will speed up the computation, right? So what it will do is it will split the data into smaller subsets and train itself on each subset, right? And this method SGD itself has also had many upgrades. So there was AdaGrad, there was Momentum, there was RMS Prop, but mainly RMS Prop and Adam are the most frequently used. Now, gradient descent is not a machine learning algorithm. They are used by machine learning algorithms to find optimal values of the parameters. Now let's see how a machine learning model exactly works. So first we will define a training set, which will have x and y, your x being your features, y being your labels. And then you import your linear regression from your sklearn library, which has all the important machine learning algorithms. You save your model in in this linear regression function, and fit it to your two variables, and return your model its predictions. Then you train and create predictions, right? So for example, I gave a new x record like 23, and now I ask the model to make a prediction based on this. So it will, obviously, linear regression will create that line, and then based on where the value for y falls on that line based on x for 23, it will predict that value. So for example, the output is 13.97. You can so mainly this is the main code for literally every model. You just need to change the name if you're using something like logistic regression. Machine learning models, though, basically use these 10 lines of code for just creating and fitting the model. So it's very easy, not much to worry about. On the other hand, if you're talking about some deep learning models, you might have to declare more parameters, and it will become a bit more difficult.